Welcome everyone to this week's lecture series of artificial intelligence. We have again another remote lecture today, and for the foreseeing time all talks will be remote. And without much further ado, I would like to give the word to Professor Mark Streit from JKU to give the introduction of our speaker of today.
Yeah, thank you, Johannes. So it's really a pleasure to introduce my dear colleague and friend, Hendrik Strobelt. So Hendrik is the explainability lead at the MIT IBM Watson AI Lab, and he's also a research scientist at IBM Research. And in his work, he focuses on the human collaboration side of interacting with AI models. And the majority of his work is actually along the lines of NLP models and generative models. And before joining IBM in 2007, he did his master's and PhD at TU Dresden. And then he moved to the US, where he worked as a postdoc first at NYU and then at the Harvard School of Engineering in Hans-Peter Pfister's group. And for his work, he also received multiple Best Paper and Honorable Mention awards at significant conferences, I think. And Hendrik is also actively co-organizing virtual conferences now recently. So he was, for instance, the online experience chair for NeurIPS this year. Hendrik, we are looking forward to your talk, and nice hat, by the
way. Hey, Mark, good to see you. Thank you, Mark and Johannes, for the introduction. Good to see you all, at least virtually. I think it would be much funnier in Linz, but this is what 2020 is about. Let me start my screen sharing. Just some technical remarks at the beginning. Here we go. I think I will make a break after each section and leave some time for questions, but I will also leave some time at the end if there are no intermediate questions. Feel free to just unmute yourself in the Zoom call, if you're on the Zoom call. If you are on YouTube, I think the comment function was just enabled, so feel free to put some text there, and I hope someone observes it and then speaks to me, because I currently don't see YouTube. You can also use the Q&A feature in Zoom. I see someone is already typing there. I will look at the question times into the Q&As. So with that said, that spotlighted your video. Okay. With that said, let's start. So what I want to talk today about is, it sounds like a pretty generic title, human interaction, collaboration with ML models. I will explain what our understanding is about this. And when I often speak in the we or our form, this refers to a whole group of people that I'm thankfully collaborate with. And this is a subset of them. I'm pretty sure there are many more people that I just forgot to put on this slide. As Mark already mentioned, I did my education on the east side of the Atlantic in Dresden and Constance, and since then I'm working on the west side of the Atlantic, former at NYU and Harvard, and now at IBM and MIT. And my expertise is in visualization, and it started with visualization for text and document collections, visual encoding. We also did a lot of work together on visualization for the sciences. And since a couple of years, I'm working on visualization for machine learning and kind of collaboration between AI and human. And from some of the projects you see here, I want to give an emphasis on these three today. When I thought about creating this talk, I also thought about Linz, and there are two AI-related connections to Linz. One is a system you might hear later in the course, or you probably already heard about it, a project together with Mark, Andreas, Peter, Holger, called Confusion Flow. And you, again, I hope you hear later about it. And the other one is an art project together with my colleague here at IBM called Form of Fluence, where we created a way of navigating a large space of sketches and trying to find out the prototypes in these sketches. And you can actually potentially physically visit it at the Ars Electronica exhibition, or just go to the website formafluence.io. So I want to start this like my physics teacher started a lecture a couple of decades ago. He came into class and he asked, "What is light?" And immediately answered, "We don't know." But we might have some explanations of what light may be. So there is this theory that light may be a wave, or light may be photons, and you can observe effects of what explanations are the most fitting for light. So, and what these are models of what we observed in nature. A model of light. And we came up with these models by first passively observing light. Sun coming down, stuff happens in water, oh, that might be reflection, refraction, etc. And then in a later stage, we were even able to control the light and do other experiments, or even bundle light, like concentrate light, if you think about lasers, etc. So in an analogy, I want to ask the question, how does an ANN work? How does an artificial neural network work? And as you heard, it's an analogy. The answer is, we don't know. So really? There are some ideas. Yeah, is it like a nonlinear statistical method? Does it do generalization? Does it memorize? Does it all of them? Is it magic? So what we try to create is, again, a mental model of how these artificial neural networks work. The problem with that is that, as the name suggests, artificial neural network, this is already an artificial model of where we try to simulate parts of nature. Yeah, and some of these examples are here. So we think of neural network models like very traditionally, like the ancient artificial neural networks were even called perceptrons. Yeah, and then we found that we can simulate some other methods that we observe in nature. For example, abstraction, if you think about CNNs, or sequences, so that we create a longer-term memory, that we create a unit that allows memorization and overriding memory, etc. And recently, we even try to simulate a method called attention, which is pretty much leaned from what we know from cognitive psychology as attention. Like where should we look at to make decisions? So I see my work, or the stuff that I want to present today, a little bit in doing exactly what we try to do for light for these kind of artificial models. So there are methods to passively observe what's happening. We might have methods to interact with these artificial neural networks models. And I want to say we go one step further. We might even collaborate with them to create a shared output. So I want to present 3 ideas today. One is how to dissect a generative adversarial network. The other one is how we could potentially detect machine-generated text. And the third one is a little success story on how we use the visualization to actually gain some pretty interesting fundamental insight. Okay, let's start with number 1. This is work together with my friends from MIT. And about a method called GAN dissection and a tool that we built on top of that called GAN paint. So you might have heard about generative adversarial networks, especially if you joined this course. I'm pretty sure this is part of why you joined this course. They are very prominently visible, and you see a lot of people using them for all kinds of purposes. So I don't want to highlight too much about how they are trained. You can look this up. It's essentially this mini-mix game between a generator and a discriminator. Nonetheless, we want to look at what comes out after training. And at the end of the training, you have what's called a generator and you have what's called a discriminator. Let's for now just ignore the discriminator and use the generator. What a generator does is it takes a random vector as input and it produces you an item out of the distribution it learned about. In this case, the generator learned about a distribution of church images. So for every random vector you input, it generates you something that has the looks of a church building. Yeah, this is what you see here. So what we did in our work was trying to look into this generator, trying to do a little bit of a lobotomy of this generator to see what has it learned about the world. One thing you also realize in the symbolic of how I draw the generator is it looks a little bit like an inverse convolutional neural network. So it's essentially, it is often based on convolutions that just get make a bigger and bigger image. Yeah? So it hence this kind of larger opening to the right. And you can imagine if you input a 100-dimensional vector and you get out a 256 times 256 picture, it's much more information to be filled with. Okay, let's talk about how to look into this generator. And don't get scared. That looks like a very complicated slide. It is actually not that complicated. So what we do is we take one layer out of this generator, here marked as R. And in this layer R, we take one unit. And for this unit, we want to figure out what did it learn about generating. And how do we find that out? Or how do we create a hypothesis for what it might have learned? And this is what you see on this slide. So we do two things. First, we create what is called a feature map. So I'm pretty sure something you will learn a little bit later in the course or already heard about is a method called saliency maps. So this is a way of finding out where does the specific unit kind of focus on in the final result. And there are 100 methods to achieve that. We just took one. Then from this feature map, we threshold the values, and what we get from there is kind of a cutout silhouette to mark in the final image what did this unit focus on? What did it put most, and I'm using the wrong word here, what did it put most attention on? Don't take attention in a machine learning sense here, more in a human focused sense. So this is path number one. So we go through the feature map and create a cutout mask. The second path we go is we just generate the image, and then we segment the image. So we say, we mark all the pixels that are tree, and we mark all the pixels that are not tree. And this is actually the whole trick, or this is one of the good tricks of this method, because you could do this segmentation with humans. That would be pretty tedious. Yeah, for 100 different categories, mark all the pixels. That's not going to work. But instead, we use a different model that was specifically trained on doing the task of image segmentation very well to help us with this task. So what we have after going both paths, we have one image that shows us where the specific unit focuses on as this kind of cutout mask. And we have a second image that shows us where are the trees in the image. And what we now do is we search for an agreement between the two regions. So we search for how much tree overlaps with where the model focuses on. And if we have a very high agreement, then maybe we have found the tree unit. And life is not as easy as I just try to make it. What really happens is it's not just one tree unit, it's a lot of tree units that actually also produce some kind of other stuff. But nonetheless, at least this is a way, if we do this very often, and we can do this very often because everything is automated, on average, we might find a good candidate where the correlation between producing trees and this unit focusing on the same area is very high. And we have a second method that I don't want to go too much into detail, where we try to make a little bit more of a causal statement, where we say, now we have candidates. So we think this is the tree unit. What happens if I switch it on? And what happens if I switch it off? Yeah, we would expect if it's a tree unit, if I switch it off, we have less trees in the image. And if I switch it on, we have more trees in the image. And again, we can calculate the causal effect, etc. What we get at the end is a sorted list of units. So we can say for producing trees, units 3, 45, bit 12, 6, they help us creating trees. Or these are the units that seem to work in this neural network as the tree units. And then we have the door unit and the dome units. Yeah. So this is cool. This is very analytical. You can write a nice paper about it. But then we thought, this is cool. But what now? What do we do with this information? And pretty quickly, the idea was born to utilize that. And this is what I want to show you. Let me switch to the browser here. Make it a bit bigger. So what we can do now is we can utilize this information and create a painting program. But it's a little bit of an unusual painting program. So what you see here is an image that was generated by the, by the GAN. So it looks pretty much like a church. And now I can start painting here on the side. So, and as soon as I release my mouse, what happens is that in this region that I just marked, I go back to the GAN. I say, in this region, please activate the tree units heavily. Yeah, and generate a new image. So if I release the button, what happens is I'm kind of drawing a tree. Yeah. And I can also do the same trick with the door units if I go here. Or I can, I don't know, use the dome units to make this a little bit more dome-like. I can even do the opposite. I can override specific units with 0, so turn them off. For example, here, the prick units. Yeah, so it looks a little bit more sandstone-y. So again, what we did is we are not painting. We are actually modifying a neural network or the internals of a neural network to generate a new image by some steering signal that we give through an easy-to-use visual interface. Yeah, and at the end, it's fun. But that's a very nice side effect. The other thing is you can try to draw a door in the sky, like do this, and you see nothing happens. Why nothing happens? Well, there are multiple explanations for this, but first and foremost, this might be a new interesting research question. Yeah, is it just because in the distribution of images there has never been a door in the sky? Or was it just there has never been a door in the upper part of an image? So how much of a context does a GAN learn actually? How much does a GAN know that these pixels are in sky? Yeah, does it really know about left and right, up and down? So the good thing about this tool now is you can very quickly generate new questions, which is always good for research. Yeah. Cool. So a little bit of a fancy animation. Yeah, you kind of change units deep inside the GAN and then generates you a new image. Okay, I want to quickly take a break here, as I promised, and check for questions. So I see that there were already some chatter going on. Thank you for the hat. Yes. Okay, seems the audio stuff is solved. Most of you can hear me. Are there any questions? Also, if you feel more comfortable asking the question in German, feel free. I can translate into English. I know how it is when you sit there.
Okay, I have a question.
Now in the chat. What is the difference to NVIDIA's GAN?
Yeah, GAN came after us. That's the major difference. No, the GAN is a little bit of a modern solution to an old problem. So this kind of creating a kind of like scene filling is something that was addressed by a lot of computer graphics algorithm, and they've just found a nice way of making it usable. And I think, from what I understand, GAN is a conditional GAN. So you essentially paint the conditions. You do not play with the internals of the model itself. Does this make sense? Philip? Is your question answered?
Yes, thanks.
Okay.
Cool.
Just unmute yourselves and ask yourselves.
Oh, sorry.
No, I think this is fine. This was answered.
Okay, cool. Any other question?
Yeah, how much processing power is required for like this process?
So the demo, as small as it looks like, it's currently hosted on a server that has a P100 in the back. So it is, I mean, GANs and inference become faster and faster, but it is also, it needs still quite a lot of power. So
Okay,
you cannot run it on a CPU only machine.
I also have another question, like to the GAN process, like there's a feature map is created, I think, and I want to know how it is created. I didn't understand.
Yeah, so in this case, I have to take a little bit the D route. I highly recommend you the paper to look into it. It is one of the saliency methods, and I honestly don't remember which one we actually use, so I don't want to say anything false here, but it is a saliency method.
Okay, thank you.
Sorry about that. Okay, so questions come in. Did you try this on Steigen generators? At the time we created this, I think Steigen was not really released. We tried it later. It turned out that ProGAN was a little bit more in our favor. In Steigen, I think we would have to change the method generally a little bit, because I mean you're creating this kind of from your input vector, you create these vectors that influence all kind of layers. So we would have to adapt a little bit in the method that we use, but it's definitely worth trying. By the way, if you want to try it yourself, all the source code for the analysis and the source code for the tool are released, so you can definitely also try it yourself. How would someone train such an algorithm? I assume you mean the analysis algorithm, so GAN dissect. Details, like very technical details, are in the source code, definitely. In general, the good thing about analyzing a generative network is that you can create a lot of samples, yeah, because you can just generate yet another image and yet another image and yet another image. So you do normally not have the issue if you want to create an analysis tool that you do not have enough samples to draw from. You have actually an endless amount of samples if you like to. I think that's the charm in working on these kind of models that can generate content. Cool. Okay. Again, there will be some time at the end of the talk to have questions. I'll just move on from here. Whoop. Okay. So speaking about GANs, one thing we also wanted to take care of or look into is what we coined as the phrase gantidotes. So like an antidote for GANs. And why would we want to do this? Well, here's a little observation, and it starts actually 2 years ago. And I apologize for this because I think technology went further. So this is output of a GAN in 2014, trained on faces. This is the same thing 3 years later. And this is another year later. And again, we are now 2 years later to that. So if this doesn't scare you, I should probably repeat it again. This is 6 years ago, 3 years ago, 2 years ago, and now we are in 2020. Yeah, so creating content that looks pretty realistic is definitely something that we have to face in the future. And this not only reflects on images. I think this is the most scary part for now, but even only just a year ago, there was this kind of news. Yeah, OpenAI builds artificial intelligence so powerful it must be kept locked up for the good of humanity. So OpenAI created a language model called GPT-2 and said it's too dangerous. It creates too good of a text to be released to the open world. Now it's 2020. They released earlier this year a model called GPT-3. These concerns seem to be gone away. It has factors more of learned parameters, and they give limited access to registered users. But what people show is that it actually can create quite some good looking text. So is it time for panic? Yeah, do we need to freak out about that? Can people now generate everything automatically? Do we have to fear what people call coordinated coordinated disinformation campaigns easily? Yeah, so far, if you wanted to start a disinformation campaign, you needed a group of trolls that flood Twitter or flood news pages with false information, and they had to create these news, sometimes often by hand, etc. So could you in future just start a bot and let it generate fake news in your favor? And well, I'm not completely pessimistic. For now, I see two kind of major directions this could go. We try to find a way to sign non-machine content. So if you make a photo of the real world, maybe you can embed a watermark that says, okay, this was done by a photographic machine capturing the real world. But this is a very large industry effort to make this kind of happening. So that we essentially switch to a mode where we don't trust everything and we only trust the things that are proven to us to be trustworthy. Or red pill would be that we have good methods to detect what is machine generated. And I want to show an idea of what could be done. This is not a solution, but at least it is an idea that other people also now took as inspiration to come closer to solutions. And this is a tool called Glitter. So when this debate around GPT-2 started, there was a famous text presented that starts with, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. This is a text that a human generated. And then the GPT-2 model took this text and completed the whole paragraph. So the unicorn text is kind of a very, very known meme now. And if you look in the internet how you actually catch unicorns, the best method is to use glitter as a bait. So hence the name for the tool, Giant Language Test Room, if you want to know what it actually stands for. Okay, very quick intro in how you sample or how you use natural language generation. And this is really the furthest abstraction I could come up with. So you start at the bottom left in this graphic, you create a start token. And the start token then is put into some form of neural network. and this neural network produces you a probability distribution about future events, or in terms of natural language generation, about text tokens, words. So it tells you after start token, word X is the most likely one, word Y is the second likely one, etc., etc. Yeah, and then you choose from this probability distribution, you make a good choice of what could be the next word, and you feed in the word again into this magic, and you get another probability distribution, and you repeat this process until you hit a stop token. And then you have generated a text. I don't want to go too much into detail. Again, what you see here is still a very high abstraction, but if you look at the same model again, so you take the start token, you find an embedding of the start token, you produce a hidden state, and from the hidden state you can infer a probability distribution. If you feed in the word again, you again generate an embedding. You generate a hidden state from the previous hidden state and your current hidden state, and you generate a probability distribution again, etc., etc. So the remaining question now is, which word do you choose if you have the probability distribution? Yeah, as I said before, at each sampling step, there are many probable events. If you think about a dictionary, if it's a word-based model, yeah, like English dictionary can easily be 50,000 words. So it's a lot of events and you have to make a clever choice. The kind of greedy strategy would be you take the most likely event at all the time. This can become pretty boring. Yeah, your options of creating varying sentences is a little bit limited then. Another option is what's called a top N strategy. So you randomly or even pseudo-randomly sample from the top N events. And another method is that you use a beam search. So you use a search algorithm on top of it that kind of retroactively tells you what was a good decision to make. Again, I don't want to go too much into the details here. What they all have in common is that they all choose from a top N part of the probability distribution. Yeah. And now the idea was to say, okay, how can we detect how likely a text is sampled from a model? Or can we detect it at all? And we can at least get some indicators, because we could actually, for each word, considering the left side context, say how likely this word would have been predicted in the top N at this position. So we essentially, for a given text, we can rerun the generation process and figure out, at this position, this word was chosen from the top 10. And we can encode this with color. So what you see here is a text that was entirely generated by using an approach to sample words from the top 10 prediction at each step. Yeah. So if you look at the first line, the following is a transcript from, let's take the word from, was in the top 10 predictions at this position, given the left side context of the following is a transcript. Yeah, and you can do this whole game for the whole text. A reason why this is called a sanity check is because everything is sampled from the top 10. But we also have other colors, as you see on top. We also have the color yellow, which says it's sampled from the top 100. Or we have the red color, which says it's sampled from the top 1000. Or we have the violet color, which says it's sampled from beyond top 1000. And this always excludes the smaller sizes. So everything that is in yellow is automatically, everything that is in green is also automatically in yellow, etc. So ignore that for now. So this is a synthetic text that you see here. If you look at the real world text, so this is sampled from New York Times, it's a very different picture. Yeah, you see a lot of red, yellow, you even see some violet in between. So how you could interpret this is that a human-made text actually chooses words at a certain position that are very unlikely under the model. So the model would not have chosen kidnapped in the third row. Yeah, like after the context of blah, 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 white woman behind the counter, he was later kidnapped. And again, it's more fun if it's interactive. So yeah, here's the same article. And if we look at the word kidnapped, let me make it bigger again. I'm always not exactly sure how much you actually can see. The more likely events at this position would have been convicted, found, charged, arrested, acquitted. Under the model, under what the model learned about the world, being trained on internet texts. Yeah. And now let's look at the unicorn text that I was talking at the beginning. So the first sentence going up to here was created by a human. And you even see that there's a violet thing here and there's red. Violet is really, really unlikely. So what this encoding also shows us is kind of how surprising is text to the model. Yeah, the more red and violet, the more the model is kind of surprised by, ooh, this word here, I wouldn't have chosen that. Yeah. So scientists at this position is only rank 1852. Yeah. But beginning from the second sentence the largest GPT-2 model was used to generate text. You see that the amount of red is not that high and violet is completely gone. So if you look at this like visual pattern, you already might get a little bit suspicious. Yeah, that's way too green and yellow and way too less red and violet. If you compare it to a human written article again, so this is New York Times. Yeah, it's much more sprinkled with red and violet. So you can even see it in the distributions of the different sectors. If you, yeah, everything gets smaller here. It's probably not so nice to see. There is another fun thing you can do if you enter your own text, which is totally possible. So I dropped my pen into the mashed potatoes. This is a perfectly grammatically correct sentence. Yeah. And you can look at this and you say, okay, you see, yeah, dropped is very unlikely, and then pen is very unlikely, meshed is like super unlikely, and it's even surprising to humans in all fairness. Yeah. But if you look now piece by piece, I think this is even funnier to look at. So I dropped what could you possibly drop? Yeah, like what is the most likely event to drop? And there's like, I dropped my first, I dropped my daughter, I dropped my phone, I dropped my kids. Hopefully at kindergarten or something like that. Yeah, not drop them. The other thing is, and this is just a secondary observation, I dropped my phone. The slightly older audience in this call might remember that dropping phones is not a particular activity in the 80s. Or it was at least much harder. You had to put much more energy into it because phones were much heavier. So this might indicate that also the text this model was trained on is like post 90. So, and we know it's internet trained, so dropping a phone is a very likely event. This was a small observation. The other thing is I dropped my pen into the, again, meshed, very unlikely. It's only rank 1200 into the water, into the sink, into the cup, into the freezer, etc. are much more likely events given the left side context. What is interesting though is that the model pretty quickly adapts even to the unusual things. Yeah, so even after this very unusual word meshed, it very quickly adapts to potatoes, because potatoes is a pretty likely event after meshed. And it's actually the top choice with a very high percentage, like 79% probability that this is the following word. There's also something like meshed avocado, meshed banana. If you want to try that, here's an inspiration. So again, sorry for playing around, but this is what we normally do. We actually did it a little bit more serious. So we gave students print out texts without any highlights and asked them to differentiate between, is this a text that was written by a human or is this a text that was written by a machine? And that was the only differentiation. And with a frightening 54%, they came up with the right answer. So chance was 50%. Yeah, so that was a little bit scary. Then we explained what our highlights do in the back, and we gave them other texts with our highlighting in the back, and the accuracy increased 20%. So this highlighting at least helped a little bit. And some paragraph that Sebastian wrote, and I think it's worth mentioning, sometimes we just do research to write papers, and sometimes we actually try to have some real world impact. So Glitter was made its round. People looked at it, news outlets covered it. They used it as a way also to talk about potential dangers of creating machine generated content, and that not all hope is lost. We even had discussions with OpenAI. They were very interested when we released that. And we have been invited to like DARPA events and even talk to like government-led Global Engagement Center about strategies for detecting machine-generated text. Again, I'm trying to avoid the word fake because fake is around since thousands of years. Yeah, I think since humans exist and create stuff, they also create fakes. The danger with these kind of methods is that we can generate these fakes with less skills and much more of them in shorter time. Yeah. So before I go on to the next thing, I'm checking the chat again. I see that the number is slightly increasing. Watermarks could also be faked. Yes, of course. This is this is well known. I mean, the general game in these kind of security questions is how can you make an attack so costly that it's not worth investing the resources anymore? There's no 100% security. That's never going to happen. Okay, so this indicates how surprised this system was. Oh, I'm repeating. So the system indicates how surprised the system was by usage of certain words by another system. What does this say about logic and training of a system? That's a good question. I don't have an immediate good answer to that. One thing that you can observe, it's if you look, for example, at the unicorn text, is that size matters. So what we use to analyze the text is a small version of the GPT-2 model. And the text that generated the unicorn text is the largest version of it. And you see that the larger model can surprise the smaller model. So it seems that really the more parameters you can train, the more human-like you get, the more surprising you can get, the more kind of nuances you can capture. Yeah. So I hope this partially answers the question. And I see these questions trickle in. I will take two more and then just continue to stay in time, and I will answer the questions at the end. but doesn't that only work if we have access to the exact model data that was used for the generation of the original text? Very good question. It does, yeah. At least we need the mechanical description of the model. We could always try to retrain it ourselves, and we like burn some trees, but this is definitely correct. So the other answer to this question is we also observe. So this is what we intended to do, to say like, okay, if you are a person who releases one of these models, be considerate and also release the antidote with them. And some people actually did. What we observed is that this thing even helps with detecting text that was generated by different models. So there is some kind of cross-pollination happening. And I say this with the biggest caution that I can put in here for some models. For other models, it doesn't work. So if you have malicious intent, it's very easy to get around that. Again, we intended this to be one way of showing if you want to be on the positive side of things and you release these kind of models, also spend this 5 days of creating a little tool that helps you detecting if your release was misused for stuff. Yeah. Then are there model-free methods currently? I should have checked recently. It's really hard to answer this question. It's a good question. I mean, you could always try to use heuristic methods that have been used before. Yeah, so everything you know about constructing language is essentially fittable for this approach. So you check. You can check, is it like, I mean, you can check if it's grammatically correct. This is something that the model normally does very well. You could try to identify if the enough resolution is done very well, yeah, or if there are glitches in that. So you can use traditional NLP methods to try to find inconsistencies in the text. So for this, you don't need necessarily access to the model. I'm not sure if this is what you meant by model-free. Quite often you use just other models to do this. Okay, I hope I answered the question. It's a little bit weird in this online setting to see if you nod or if you shake your head. Let me continue, and I will come back to the questions after finishing the talk. Okay, last thing I wanted to show is a little tool we created that we initially didn't want to create. So this is a tool that allows you to look into transformer models. Again, you might have heard about them. They are the cool hip shit at the moment. This little tool we created is called Expert. Like expert, just with B, which makes it very hard to find, we realized later. So quickly, what are transformers? Transformers are deep learning architectures that use what is called self-attention to be really state-of-the-art in many NLP tasks. And what self-attention is depicted on the right side. So if you want to make a prediction for the position that is circled in green, the model tells you maybe you should look at contexts like dog, shook, room, etc. And then you can predict it with bark. Again, very oversimplifying what's actually happening. Also, transformers do not learn only one attention. They learn a lot of these attention correlations. So typical example is, the moment I started, I forgot the name. It's 144 attention. So 12 layers of 12 attention heads. What was the name of the, damn it. Okay, if it comes back, I will tell you which model I refer to. But this is essentially the core idea. Yeah, that you essentially have a way of predicting a specific position by kind of creating the weighted sum of embeddings that you look at. This is a schematic, and again, I don't want to go too much into detail, but this is essentially showing like how one attention is calculated, and then you take this into a block with other attentions with some normalization in between, and then you take this block and create a block of blocks. So it's not only attention, but it's also a hierarchical arrangement of these attention that make this whole thing work. And this is like how the tool looks like. So for each word here, you see essentially what it attends to, and you can select layers and attention heads. So you can essentially make a selection out of these 144 models. Out of these 144 attention mechanisms. The other thing we added is a little bit of a trick to understand how these embeddings that are produced can be interpreted. So for each word, as I said before, you create an embedding. And to understand what this embedding might mean is, we took a reference corpus, we piped it through the models, recorded all embeddings, and then for a new example, we can actually look for the nearest neighbors of embeddings and see if there is some kind of alignment between them. So see if the encoding for the word bark, the embedding for the word bark at this position is close to an embedding of a reference corpus for the similar kind of context embedding. But the most important part is we can look into what does, for a specific position, where do we focus on to make the prediction at this position? And now comes the actually funny story. We didn't want to create this tool because at the time we created it, a lot of people were already talking about transformers, and there were some simple versions of this already visible. But by creating the tool, we actually got approached by one of our colleagues who was training a bird model on chemical reactions. So chemical reactions, you remember from school, this is how this stuff looked like. Probably a little bit simpler than that, but core principle, same. And you can express these chemical reactions in what is called SMILE strings. So there is a string representation how you can encode chemical reactions. And this is how they look like. And as you can already infer, string, sequential data, maybe this is something where a language model or an NLP model could help with. So we use a SMILE tokenizer that creates us words or tokens out of this SMILE string. And this is what we feed as kind of language to the model. So we learn the language of chemistry or of chemical reactions. And then we use our little tool to look into what has the model actually learned. Like where does it attend to when it makes predictions? And we looked into this kind of head functionality and figured that for some of the layers in the model, this model learned a function which is called atom mapping. And atom mapping is a function that tells you which atom from the input maps to which atom of the output. So you take a carbon in a benzyl ring here, and you want to know where did this carbon end up in the product, in the chemical product at the end. And this is a very complex problem. People have researched since the 1970s to come up with like sufficient heuristics to get this atom mapping right. A lot of postdocs have been spent their time in creating these complex heuristics. And we just figured that the neural network model might learn about this function to a pretty good state. So what we did now was adding a little bit of a small modification on top, created a tool called RxN Mapper, and ran it on top of a set of chemical reactions. And this is just a projection of the different reaction classes. Again, not too much detail, but we got pretty close to the state of the art. Yeah, and this took us not a lot of time. State of the art is a commercial product that has been developed for years. Yeah, so I think that's pretty cool, because even in research, it is not very often that you have very surprising insight. Yeah, in this romantic world of 19th century research, you always have surprising insights. That's not how it works these days anymore. But this was one of the examples where we really had this epiphany effect. Okay, trying to sum up what I just showed you. So the lessons learned on a soft level. For GAN paint, I think it is really fun to use interactive tools to gain insight, but they also can enable collaboration between human and models. So remember the example, I can try to force the model to create a door in sky. If the model doesn't know about that, it just doesn't create it. So it's a constant negotiation between model and human to create a shared output. Yeah. Again, glitter, don't be afraid to build a tool. It might not be the final solution, or it might not help you on a large scale. Yeah, so you cannot use glitter to run through all kind of texts that are produced to answer the question. Yeah, you can take it as inspiration and say, okay, I make a much better algorithm to do this. And actually, people who reference glitter do much better solutions now. Yeah, but it's nice to see that you can at least inspire some thinking. And kind of an epiphany I had for using expert on chemical reactions was that you can utilize neural networks actually as a pretty sophisticated statistical tool as well. Yeah. So if you imagine we would have taken the SMILE strings and just ran our simple statistic, yeah, like averaging, accumulations, etc., we would not have found out any intrinsic information with respect to atom mapping. This is a much more complex function. But by using a much more complex statistics to find out this complex function and using visualization to uncover it, we were able to achieve this insight. Yeah. So, and I think there are quite some examples now where neural networks were trained unsupervised, and people looked and dissected them and figured out what these networks have learned about their presented real world. And it is pretty surprising. Yeah. That's pretty fun. The iceberg remark. What I showed you are the kind of successful examples of what we did. Be aware that most of the work we do is under the waterline. It's the stuff that you don't write a paper about, yeah, because it didn't work. It just didn't play out. So if you start doing some research in these directions, don't be discouraged. Don't be discouraged if your ideas don't work out. Yeah, this is all. Sometimes something bubbles up above the waterline. Yeah. And one more other thing is, I really want to encourage you to do stuff, to create your own little tools, to be able to realize your ideas in code or something, because I really believe that thinking does not only happen up here in your brain, it also happens in your hands or in the nerves that attach your hands to your brain. Yeah, so I can only encourage you to create your own little like framework that helps you to create one-day prototypes, where you really in one day you can implement a small, stupid, funny idea. That's what I try to do. One example here is just recently I created a tool that uses GPT-2 to create you excuses to say no. Yeah, should I attend the meeting? Pipe it through GPT-2 and let it finish the paragraph. And I actually love the last answer, say like, no, I must not attend the meeting because in my opinion, the meetings should not take place when the Pope is absent. And it just got accepted to the NeurIPS Art Gallery. With this said, I let the tool answer this question. Thank you for your attention, and I'm happy to answer as many questions as we have time for.
Thank you very much for this very interesting talk. I would like to ask you to unmute yourselves and ask questions.
There are a couple of them in the chat still. Yeah, maybe let's start with the live questions and then I go into the text. If that's...
Any questions via audio?
Again, feel free to ask them in German if English is too hard. I can translate.
Yeah, how do you actually like working at IBM and working in America in general?
Yes, so that's a good question. I like working at IBM in IBM research. I think if you think about a little bit the history, it's one of the few places left where you can actually do kind of academic research in an industry setting, where you can have crazy ideas, yeah, and don't need all the time to justify industry impact. I mean, it's important that you create stuff as well that helps the company to flourish, but you can also do fundamental research. And I think there are not a lot of IT places left that allow you this kind of freedom. So that's what I like about being there. Also, this very large collaboration with MIT is definitely fun. Living in the US, I think the answer is a little bit different this week than last week. It is, again, I lived in New York and I lived in Boston, which is a very different experience than living in the middle of Texas. So the experience I had is pretty fun. I think the major difference towards Europe is, I think in Europe, people often think more before they do, which has its benefits and its quirks, because with thinking, you can also kill ideas pretty quickly. You can end up in a loop where you say, this is trivial, let's not do it. And then you try to do the trivial thing and you figure out it's not that trivial. Yeah, actually, it's much more complicated. So yeah, no, it's fun. Yeah.
Questions?
Yeah. I have one question. What do you think about this incident which happened at Facebook, where two different AI agents like created their own language, and then I think they shut it down? What's your opinion on that?
Funny enough, I didn't read about it, but I think it is a very interesting experiment. I mean, it is very fundamental in its core to see, yeah, how, I mean, imagine if you observe that, you might actually learn something about how we at the end came up with something that allows us to talk about things. Yeah, so just much more rapidly, because we don't have a couple of million years to observe like how these two models talk to each other. But can you quickly elaborate like why they shut it down? I should actually read this up. Why didn't I know that?
I can post a link, maybe.
Yes, that would be great.
I think they shut it down because it didn't do the task they were asked from it. because it just invented a new language and they wanted to, I think these two AIs should trade in a human language, and they didn't do the task, so they shut it down because it found more efficient way to communicate, and they wanted it to communicate in the human language, and they was like, okay, it doesn't communicate in the human language, so it's not really useful for this purpose.
Yeah.
For other purposes, maybe it is useful.
Oh, that's so funny. I mean, this is. Thank you for hinting me to this. I definitely should give it a look. It's. I mean, there are so many sub stories that you could think about building up out of this. Like how much redundancy is in language, how much non-information content is in language. You know, like these kind of questions. Cool. Yeah, thank you for this link. That's really fun. Are there any other questions or remarks? Again, I see a lot of text here and I will go through them in a second. I just want to give.
I have another question about glitter. I think, is it good at getting or analyzing information if somebody is not really fluent in that language, or it has a better language level than, I don't know, some New York Times things or something like this? If you're not good at the language, you often use simple words that are logical to connect. And can glitter, is it then even a useful tool or not? Because, for example, in elections or something, if a troll doesn't have, I don't know, the language skills or something like this, was it useful for that or not?
Kind of. The reason I'm smiling is because I always say, like, if the text you produce comes up as green and glitter, you should definitely take some language course. No, I think it very quickly symbolizes or shows that the texts that come up as very likely in glitter are also very, very boring texts. So they miss the surprise. They miss this kind of narrative element that we call like a surprise, or that we call information. Yeah. So what these models often really learn is the average language, you know, like with nuances here and there, and it can be a little bit more flourish, but at the end, they learn average language, and average language is pretty boring. Yeah. So again, if you write a paper and we did this for fun, you know, like take your abstract of the paper, paste it into glitter. If if everything's green, don't submit the paper. Yeah, like you will get a reject. What this opens, on the other hand, as an opportunity is to use this kind of idea to detect like the important part of a text. Yeah? So everything the model is surprised about is potentially where the information of your text is hidden as well. So you could even think of using it for some kind of knowledge extraction method. And again, nothing of this is solution. It's all just play around with it, get inspired, and then make a really good paper for that, or like make a real good system that does this better than glitter does.
Okay. Maybe my question is a bit naive, but
No.
do you think that every AI and like its output can be understood and retraced? Or do you think they're like, even in theory, just in theory, or do you think there are like some AIs that behave so erratic that they can't be understood and the output can never be reproduced?
That is a very good question. I mean, it's probably too early to answer this question, because currently we even have trouble doing it for specific models where we think we can have control over somehow. I like approaches that are also very current, where you say, okay, in an unsupervised setting, we let the model learn some kind of random stuff that we don't care about, but we also let it learn about factors that we know about. Yeah, so the latent variable models are a good example for that, where you say, model, I leave you some space here for random learning stuff, but for like this part of you have to learn something where we humans already give you a hint of what this should be. I think that is potentially how I can see that, how we end up saying like, okay, part of the model is inherently interpretable and part of the model is just like, do whatever. Yeah.
Thank you.
But ask me in a year again and I will give you the complete opposite answer. Maybe I go quickly to the text. Did the RxN mapper help in research for Corona? No. We also had 2 other projects that actually were in the context of Corona. So we trained a Wasserstein autoencoder, an unsupervised method again, using some clever selection technique, which kind of hyperparameterization to choose, to generate candidates for treatment of COVID-19. In combination with AstraZeneca, and they actually took some of our molecules to test them. And we had another project together with the UN, United Nations. They had an agent-based model to simulate spread of COVID in refuge camps. And we just released this a week ago, and we created some visualization to look into the results, less into the model itself. This will be the next step to see what has the model learned about the dynamics of spreading COVID. That was the link, thank you. There has been some research to introduce radioactive markings in images generated by GANs. Do you think such a thing is possible for text? Has it been done? Second question, I currently cannot answer. First question, yes, I have hope that this is possible for text as well. I think in the simplest case, or I think in text, you also have control over how you encode information in a similar way as you have control over encoding information for images. So under that, if you take this as a lemma, I think this is possible. It might need a little bit of clever encoding. Yeah. The question is, what would you gain? So, Jules, I'm not sure if you're on the call. That would be interesting. I think I can imagine this for translation tasks so that you have correspondence between original language and target language. Yeah, that you say, okay, here are some markings that show you this refers to that. But yeah, I would love to know what you think would be the benefit of doing that for text. Meanwhile, I go on. Feel free to interrupt me anytime. When you improve GANs over time, don't you get an automated improvement of the discriminators as well? How is Glitter better than the discriminator trained by the GAN? Glitter is not for GANs. Glitter is for language models like BERT or GPT-like models. So they are trained on different tasks. For images, you could think of a similar technique, and then I agree. Then you should definitely look into the discriminator and see if they help you. One little experiment we did is we trained. So if you imagine you want to detect like fake images or machine-generated images, another option you could do is you can train an encoder, so a model that allows you to take an image and find the Z that comes closest to reproduce this image with your with the generator. And then you can essentially see if you how close you can come in the distribution of the images it learned for your input image. So how well can the generator reproduce your input image? If it can reproduce it very well, then it might have been generated by this generator. So this is essentially kind of using the same kind of idea for images. But I agree, if you use a GAN discriminator, is definitely something you should utilize. What would it mean for your method if one sampled from the whole predicted probability distribution and not just the top words? Why is sampling not done in this rather straightforward method? Well, if you sample completely randomly from all potentially predicted events, then you wouldn't need a model in between. You would just constantly roll the dice and sample something, and you would not get a coherent text. If you would sample from the whole distribution, adhering to the weights, so giving like higher rates, a higher probability to actually be chosen in a completely random process, you might still end up in this scenario where you create probably more surprising text, but actually really surprising text that is very easy to detect by humans as like what does this tick here in the text actually mean? Yeah, like what's going on, what's wrong? So it's this fine balance of creating coherent text to fool humans and creating coherent, surprising text to not bore them to death. Yeah. So, and I think this is this balance you go on. And again, I'm not sure if I can give the talk in 2 years' time if GPT-10 is around and it captures the whole library of humankind. Yeah. No, I actually want to stay away from making predictions in that direction. What if we tune the temperature parameter to match the green, orange, red, purple distribution? Good question. That's definitely a possibility. Yeah. So glitter is not foolproof. Would be fun to see the results. We could learn that. Sorry, we could learn a pattern of top K sequences for sampling that is typical for a human written text, right? Yes. So you can definitely play the game of saying, let's try to learn something that glitter cannot detect in that matter. Yeah. There were some 3 recent questions. All right. Do you think one-shot learning can be applied to NLP? I think you have very good people in Linz who can answer this question in a much more better and theoretical way than I can. I hope so. It would be fun. I think there are some approaches for images that go in this direction. For text, let's say I have my doubts. Don't look in this video in 2022. Yeah. So, and the doubts mainly come from the idea that text is already a human-made abstraction for describing thoughts. So I'm not I mean, take nature as an example. I'm not sure if you can try to get a baby to like learn language from presenting it a sentence. I mean, it has struggle like matching real world objects to names. Yeah, like mama, papa. So, but again, premature thinking. Ask me in 2 years again. You could gain a way to recognize a text generated by a given model without the need for the model itself. At least for the GANs, they hope to use it for fake detection. Oh, this is already an answer. Okay, yeah, thanks, Jules. Do you think there is a model out there or a technique that to distinguish between fake news and real news? The reason why I was very careful, and I think I mentioned it at the talk, to not call this fake text and real text is fake news is a multi-level problem. Yeah, like it could be like machine-generated text. It could be human-generated, but completely false statements. So I think there is no model out there that does this coherently. I know that there are certainly efforts going in this direction. So there are, for example, there's a DARPA project that tries to find inconsistencies in multimode representation of data. So for example, if you have a news article and you find an inconsistency between the images shown and the text describing. Yeah, if the text talks about people rioting in the streets and you see like a couple of grandparents holding up shields like we want more pension, then you have a kind of a discrepancy between what the text describes and what the image shows. Yeah, and there's some efforts to go in this direction of trying to find logical incoherences, especially if you have more than one mode of representing information, yeah, like between image, text, etc., or different texts even. Cool. Oh, Mario said a good link. Thanks for the link. I think that essentially concludes the text chat. I hope. The problem is I cannot save this text chat easily, I think. Let me try this because there were some really interesting remarks in here and I hope I didn't skip any or too many.
You can copy paste it, yeah.
Yeah, I just did. Thank you very much. Cool. Are there any
further questions via audio?
Yes, I have one more question. Thanks, Hendrik, for the talk. You showed a lot of tools where you can interactively play around, and also mentioned that it's important to just get started and play with things. How do you usually approach that? Because adding interactivity to something is also always a bit tricky.
Yeah,
especially when in Python, for example.
Yeah, I agree. Life gets better over time. That's one observation. So there are some people who really spend time in creating frameworks that make these kind of tasks easier. Yeah, so for NLP, for example, and I'm not getting paid by them. I just get stickers from them. There's a company called Hugging Face, and this is actually their official company description. They spend a lot of efforts in trying to make NLP models easier to create and easier to use. Yeah, so you can, for example, let me show you one quick example, if I may. This is a little bit more spontaneous. So this is, for example, something I did for a course at MIT, where you can also look into the attention heads, and you essentially just map the attention values on some heat map. First, you can look at this repository that's open source. Yeah, you can easily, I can send you the link. And if you look into the source code, let me, maybe that's not the best. that's not crazy. Yeah, I mean, it's well documented as well. So we take the lines of documentation off and you have a very short way to get into these models by using this kind of helping libraries like Hugging Face. Yeah, you can even create a very simple sentiment analysis tool with a two-liner using a Hugging Face pipeline. So I think one recommendation is, this is a general Python recommendation, I think, search for the library first that solves the task you want to do. And only if you don't succeed, try to do it yourself. But do one very thoroughly, yeah. So that's probably a good thing. The other thing is, and this is what I mentioned as well, over the time, I really created what I call the secret weapon, which is a little repository that has already a setup of Python backend and some connected to a JavaScript front end. And I just check out this repository, change 2 or 3 files, and I'm ready to go. Yeah, so you spend all the overhead in setting up yet another new. I mean, the hardest is to start from white page, yeah, to start from nothing. This is normally, this is where you have to get up in the morning and be very motivated. It's much easier to start from something that you know is already connected, and you know, you just need to change this and this and to implement such an idea. But you have to do it yourself because it aligns with how you are thinking, like what is your best method of doing it. So, yeah. Okay. Does it help?
With an eye on my watch, I suggest we come to an end unless there's a last urgent pressing question, final chance. If not, thank you very much, Hendrik, for this fascinating talk and for so patiently answering all the questions via audio and also from the chat. I thank you all very much for participating. Thank you, Mark, for the introduction in the beginning. Hendrik, if you send me your slides, I will also put them available for our students. And with all this, thank you very much again. And to the students, see you next week. Bye-bye.
Thank you also. And I'm looking forward to have some coffee at the hipster place in the lake. I really enjoyed it
sure.
Cool.
Thank you, Hendrik.
See you soon.
Thank you.
Bye-bye.
Bye-bye.